All right. Hello, everyone. Welcome to the first iOS workshop by GDSC, the Google Developer Student Club at SFU. And today we'll talk about the essence of iOS development. Before we begin, I'd like to introduce myself. My name is Jenkins, and I'm a two-time winner of the Swift Student Challenge. I hope that after this series of workshops, you will also participate in this competition. I'm looking forward to seeing what you will create. Today, I don't want you to listen to this talk from the perspective of an iOS developer learning new APIs, but rather from the perspective of an API designer. What this means is that we will go back in time to before any development framework existed and imagine that you are an Apple engineer starting from scratch to design a framework for iOS developers. I believe that after this, you will have a much better understanding of why the frameworks of today look the way they do. Before we proceed, I want to clarify that aside from the demo part, we will not see any real APIs today. Also, everything will be simplified or slightly different from reality to help you understand the content. So let's get started. The first thing we need to provide to our developers, or perhaps the first thing developers want, is the user's input. For iOS developers, this means touch input information, like taps or swipes on the screen. And how do we pass this information to our developers? Let me give an example, which you can pause and think about after for the other types of gestures. For tap, we could have developers implement a method called maybe handle tap. And in the argument of this method, we would pass the x and y coordinates of the user's tap to our developers. Now, think about what kind of values a developers would need for a swipe gesture. Maybe every time the screen samples, we could tell our developers where the user's finger was before the last sample and where is it now, so that they could write functionality, for example, like dragging. And sampling just means that the touch module quickly scans to detect the position of the user's finger on the screen, and it is often at a speed about twice the screen's refresh rate. Another piece of information that might be useful is when the swipe gesture stops, just like the timing of it. Imagine our developers are writing a module like scroll view. They would need to know when the gesture stops and possibly the speed of the gesture at the time it stops, so their animation can maintain a certain inertia to make the animation look more natural. Now that we have gestures inside our toolbox, our next basic framework, I would say, is rendering. Or more precisely, lower level rendering. Because we need a rendering framework to draw UIs for the user and to create animations. And in actual app development, we almost never directly touch such low level rendering. So if the next little bit is not very understandable, it is totally okay. But I still hope you know about the existence of these low level frameworks, so you have a deeper understanding of some of the behaviors of the actual higher level frameworks. Now let's shift our focus to this little thing called a layer. A layer, to some extent, is like a canvas where we can decide what to draw inside it. The first question might be where this layer should be placed on the screen. We need to figure out how to let our developers specify a position or a location. Borrowing the concept from mathematics, we can define a coordinate system and use the top left corner of the layer as a reference point and call it the origin. This might be slightly different from the coordinate system you've seen in mathematics because its y-axis is reversed. It's increasing from top to bottom. This is actually a traditional way in computer rendering, said to be related to the imaging principles of old-fashioned monitors, and iOS naturally followed this system. However, macOS is different. Its y-axis is actually the opposite, just like in mathematics, with the arrow pointing upwards. So back to our iOS example. To change a layer's position, we just need to change its origin. This is exactly the same as defining a point in mathematics. Now that we have coordinates and units, our second question might be, how do we let the developers define the size of this layer? This is also quite simple. We only need to define a property called a size, and by changing its value, we can define its dimensions. In fact, for some elements, we can even directly calculate their size. Like a layer rendering text, if we know the context font and the layout information like spacing, line spacing, character spacing, we can completely automate the calculation of the size value. With one layer, you can really do so much. In most cases, we will be using more than one layer, and the position of this layer is often relative. For example, this small square may need to be 10 pixels from the left and 10 pixels down from the origin of this large square. We could also calculate the exact value by adding the origin of this outer square to the inner square using vector additions. But in programming terms, if we do this, we will be exposing extra information to the inner square. And if the position of the outer square changed, we would have to recalculate the position of the inner square. So how do we solve this problem elegantly? And one of the solutions is to establish a local coordinate system based on the origin of the outer square, and use this local coordinate system to position the inner square. This way, developers would no longer need to worry about the mathematical calculations and everything. Like, just imagine this square might also need to rotate, right? So our current coordinate system structure is actually something like this. And at the top, we have the root view, which is just a large range of the entire screen. And inside it, we have the outer square, and within its coordinates, we have the inner square. And this system still applies when there are multiple layers. All we need to do is just to add new nodes into it. And correspondingly, this is a data structure we might have learned in a class like Compute 225, a tree. So we also call this system the layer tree. And now let's return to the simplest single layer case. If you have taken course related to computer graphics, then you might know that we can perform various transformations on a graphical element. And at the most basic level, if a developer wants to move or rotate a layer, they can do something use matrix multiplication. And if you're not familiar with the math here, don't worry. We almost never use this matrix directly, but considering some in the audience may be interested in this concept, we'll quickly go over it. First, there's this form of the matrix. We can change the position of the content within the layer by altering a few entries. And in this case, there would be the tx and ty and tz. Notice that I set the content's position and not the layer itself. And in practice, we can design a simpler API for our developers, and allowing them to achieve the desired effect by simply giving us a few different values instead of changing all the entries inside the matrix instead. And similarly, we can do something like rotations. And of course, developers can accomplish this by specifying an angle directly. So returning to the layer itself, we haven't yet answered the most important question, and that is, what exactly do we want to draw inside this layer? In the era where object-oriented programming was the most important thing, right now it's still important. Our solution was, of course, to define a layer as a class, then define a draw method to let developers or ourselves override it. And implement corresponding drawing logic. Our reason for writing this or to implement the draw method is, of course, we want to define some of the most basic rendering logic, such as text rendering, image rendering, and maybe primitive shapes rendering, and etc., allowing developers to skip this part of the work or even keep them unaware of the existence of the draw method. So if we get some text-related information through some, say, dependency injection, then we can use the string data for text rendering. Or if we receive some parameters for shadow rendering, we can also detect it here and draw the shadow. You may have noticed that the shadow is not within our frame, which indicates that our canvas is not limited to just the selected range. So this part is about the underlying rendering content. If you want to learn more, you can search online for keywords like core animation. It's okay if you didn't quite understand the specific details. I just hope that you know the existence of layers and their significance. Next, we need to combine these two powerful tools in our toolbox into something called a view. Because the two things we just talked about are kind of separated, and this has a lot of limitations. For example, if a user clicks or taps somewhere on the screen, if the rendering is completely separated, developers would have to determine if the tapped area is the particular button. I hope you remember the following two equations. Views are essentially equal to the combination of gestures and layers. Or you can say that they are just wrappers of these two. Well, when we talk about layers, we're merely referring to the underlying rendering. So with just rendering inside a view, we can create many different standard views, like labels if we have text rendering logic, and pictures if we have image rendering logic, and of course basic shapes like rounded corners. And if we combine the judgment of taps and drag gestures, we can create some things like buttons. Say you tap on this text and we detect that it's within the area of this button, then we can trigger some actions. And we can also create something like the toggles or switches and segmented controls, for example, and many more. The advantage of defining these standard components is that if we add features like accessibility support to them, then developers who use these components can not only quickly create interfaces, but also gain these important features as well.